Chlorine is everywhere, in our pools, disinfectants, and even the salt we eat. But what makes it so useful? In this video, we'll explore how chlorine's atomic structure and electronegativity influence its ionic and covalent bonding, and how it can be applied to the real world. To get a complete understanding, we'll cover chlorine's atomic structure, including its subatomic particles, electron configuration, and isotopes, electronegativity and how it affects chlorine's ability to form ionic and covalent bonds, examples of chlorine compounds like sodium chloride and chlorine gas, and uses and properties of these compounds and how they influence everyday scenarios. Chlorine is in group 17, the halogens, one of the most reactive groups of elements. It's in the third period, meaning it has 3 electron shells. Because of its position on the periodic table, chlorine's properties are influenced by it, possessing certain trends typical of nonmetals, such as its small atomic radius and high electronegativity. Chlorine has 17 protons, 17 electrons, and 18 neutrons in its most abundant isotope, chlorine-35. Its electron configuration is 287, and this is its SPDF notation. Chlorine occupies the S and P subshells. 1s, 2s, and 3s are fully filled with 2 electrons each. 2p is completely filled with 6 electrons, while 3p has 5 electrons, leaving it 1 electron short of a full octet. This makes chlorine an extremely reactive element, as it readily attracts electrons. Chlorine exists primarily as 2 stable isotopes, chlorine-35 and chlorine-37, and it has an average atomic mass of 35.45 amu. At room temperature, chlorine is a greenish-yellow gas with a strong choking smell. Its atomic radius is about 79 picometers, and it has low melting and boiling points. Chlorine's density in its gaseous state is around 3.2 grams per liter. In terms of chemical properties, chlorine is a highly reactive element, reacting with metals like sodium and nonmetals like hydrogen. This is why chlorine is widely used as a disinfectant and bleaching agent. Chlorine has an electronegativity of 3.16, meaning it strongly attracts electrons. This is central to how it forms both ionic and covalent bonds. It also has a core charge of +7, indicating a strong attraction between the nucleus and valence electrons. Chlorine's first ionization energy of 1251 kilojoules per mole means it takes a lot of energy to remove an electron from its outer shell. Chlorine tightly holds its electrons due to its small atomic radius. Ionic bonding in sodium chloride occurs when sodium transfers its 1 valence electron to chlorine, which has 7, completing its octet. This results in sodium being positively charged and chlorine negatively charged, forming an ionic bond due to the difference in electronegativity. And this is what gives us table salt, the ionic bond that makes NaCl so important in everyday life. In NaCl, oppositely charged ions form a rigid crystal lattice structure, where each ion is surrounded by opposite ions, like puzzle pieces. When pressure is applied like this, ions of the same charge repel, causing it to break, which demonstrates its brittle nature. NaCl has high melting and boiling points due to strong ionic bonds. It dissolves easily in water as the opposite charges of water and salt ions attract each other, causing dissociation. Water molecules pull sodium and chloride ions away from the crystal, making it dissolve. Real-world uses of NaCl include cooking and food preservation, helping to reduce moisture and slow spoilage, de-icing roads by lowering water's freezing point, preventing ice from forming, and medical saline solutions for rehydration, nasal sprays, and cleaning wounds. Covalent bonding occurs between 2 nonmetals like chlorine, each with 7 valence electrons. To achieve a stable octet, they must share 1 electron, forming a bond. Both atoms have identical electronegativities, meaning they share electrons equally, resulting in a nonpolar bond. Cl2 is a diatomic molecule consisting of 2 chlorine atoms bonded in a linear structure, with both atoms completing their octets. This ties back to its nonpolar nature as it lacks a net dipole moment. Electrons are constantly in motion, and at any given moment, they may become more densely packed in one area, creating temporary dipoles. These dipoles result in slight attractions between neighboring molecules. The opposite charges between the dipoles create an attraction called a dispersion force. Since these forces are weak, it requires little energy to overcome, which is why chlorine has such a low boiling point. Chlorine gas is essential for disinfecting water in drinking supplies and pools, killing harmful microorganisms. It's also used in PVC plastic production for many everyday items. However, its toxic and corrosive nature transformed it into a lethal choking agent in World War I. I created a 3D animation in Blender to visually represent the chlorine atom, the ionic bonding in NaCl and its lattice structure, covalent bonding in Cl2, electronegativities, and more. The animation represents protons, neutrons, and electrons with spheres, and electron orbits in rings, further enhancing detail. My Blender model offers a cohesive and engaging way to understand atomic structures and chemical bonding. Unlike static physical models, Blender provides a more flexible way to animate the processes of electron transfer and bonding. It also allows for easy modification of shapes, sizes, and colors, making it highly customizable without the limitations of physical material. However, while a physical model offers a hands-on experience, the 3D model is limited to screen interaction, which eliminates tactile engagement. Additionally, the use of spheres and rings may oversimplify the complex state of atomic structures and bonding, potentially giving the audience a misleading representation. So after countless hours of editing and learning Blender, this is what I came up with. Thanks for watching.